214? Yeah. Well, let's dig in there. I think we spent enough time looking at we spent a lot of time looking at the financial functions. Like we got all 6 of those nailed. I don't know. Those should be things that you probably just think about, lie awake at night about, wake up in a cold sweat about. I don't know. I know I do sometimes when I'm trying to figure stuff out.
I looked at it and said, yeah, I'm just going to go to class.
Okay. Well, I hope I am of some help. I figured I would just try to catch up to wherever you guys are or are not. Yet. Week five. Tell me where I should head. Week
5.
First click.
Yeah.
Power factor fees. Oh yeah. Okay. So it sounds to me like the power factor in 213 needs to happen before it does in 214, because we haven't really covered that in lecture in 213.
Or in...
However, I have some additional form exercise to get the power factor and reactors. Okay. One method, charges for peak. 15, calculates peak. All right, so Fraser and I just need to get on the same page with power factor then.
Yeah, if you can do that, that'd be great.
Yeah. The third uses a monthly power factor, kilowatts. Okay. Some threshold, demand, okay. Nice. So is it better to cover power factor for a half hour and then look at the power factor charges after that? Would that probably be the best?
Since we only have 2:30, because 2:30 is when AC Circuits Lab starts. So you could do power factor and then spend some other time without us doing the Excel. Because I'm just having a hard time. Like, I looked at it and downloaded that little deal or whatever.
Mm-hmm. Oh, yeah, let's look at this. We can look at this guy. Download the power quality teaching
tool. You don't have
tool.
a file decompressor on your computer. It's going to be a pain to download.
Well, maybe we won't mess with the toy for now. Let's just go back and...
That part wasn't too bad.
Yeah, because I guess I just really want to know, because the first one goes into...
That's actually a pretty good diagram, the horse pulling. And that's very similar even to the phasor diagram we just went over. And that's the apparent power is always going to be greater than or equal to the real power. The only time it's going to be equal to is if that angle is actually 0. Let's look at, this is a good one too. Cause of low power factor. And I even have a, file, close.
Jesse, did you do anything with number 2?
Problem 2 this week?
Yeah.
No, that's it.
I mean, I barely, I literally just put that information in there because I was confused.
Guys, here's, I just want to show you this really quick. I know in 213, well, you guys have covered resistance all day long in DC circuits. That's the first part over here. That's your resistance, there's your current. You multiply resistance times current, you get voltage on the right-hand side, right? There's your V equals IR. We've talked a little bit, or the book, we haven't really spent much time in lecture, but the 213 book talks about capacitance. That's the part on the right side. And so this little C here actually is capacitance. This funny looking S is the integral sign. And what that says, if I am adding up, that's all you're doing, is just adding up current going in the capacitor, that's all it does. And that funny little S sign is the sum of all the current going in there. If I just add that up over a certain amount of time, however long it takes those electrons to get in there, divide by the capacitance, I'm going to get the voltage. And here's the other part of that. So those are your two of your elements, your resistors and capacitors. The third fundamental unit in any electrical circuit is the inductance. What's the inductance? Well, you can think of it even back to what we were talking about in 213 a second ago. It's that big long coil of copper. Could be in your transformer. Typically, though, it's in your motor. It's in your compressor motor in your fridge, your motor in your table saw, whatever it is. Big, long coil. You know, you've even got one sitting right here, this funny little wind turbine we built a few years ago. Coiled up wire. So you've got basically a racetrack of electrons racing around. You've got, well, I-90 is not a good example because it's never busy, but you've got I-94 in Michigan with 10,000 cars backed up, and they're going, and then one of them stops, you have a big pileup. So that's your inductor. That's the L in this equation. And what I've drawn, and again, you've got I here for current, you got I here for current going through your resistor, and then you've got I here. So current and voltage are common. The three things that change are your resistor, your inductor, your L, and your capacitor, C. Now, the one thing you might have missed is this funny little dot over the I. What's that dot mean?
So, rate of change.
It's the rate of change. It's the same as that dt we looked at in Maxwell's equations. It's how quickly that current is changing. So in an AC motor, that current is sloshing back and forth, back and forth. So that the dot is telling you how quickly electrons are flowing back and forth in the pipe, in the inductor. And that is basically the reason why the power factor thing exists. Because it's you can think of it as an inefficiency in a system. Just like everybody on the interstate out there kind of like accelerating and hitting their brakes all the time. It's just wasted energy. So, hey, no, we're going to accelerate. No, we got to stop. No, we're going to stop. Now we're going to stop. Same exact thing. It's wasted energy in your system. Does that make sense? Just kind of analogy for what power factor is. So why improve it? Utility bill will be smaller. A poor power factor means that the electric utility has to be bigger because you've got these inductive loads, and again, the inductive loads are those just sloshing electrons like I just talked about, and you get penalized if it's bad. And this is exactly what SATIC is doing right now on their home systems. in 214, we're talking about, large industries, giant motors being penalized for big power factor losses. It hasn't happened in this country yet, but in Europe, if you've got a bad power factor on your house, you're going to get charged too. So maybe it'll come here eventually. All right. So is that a reasonable, and is that a reasonable enough coverage of power factor to kind of know what it is? Oh, you can see that what they've done in the circuit is added capacitance, and it's a little bit like, well, let's think of it this way. If you've got all those cars racing towards each other, and one person slams on their brakes, the capacitor is just a wider lane. You've got little places for the cars to pull off and not have to hit their brakes, so they can then join the traffic. You've added more capacity to the highway system. So you throw some capacity. You're just putting little electron buckets in your system, so those inductors that would be sloshing the electrons around, now they go into your capacitor. So that's how you fix it. You fix too many inductors with a few extra capacitors. You fix all your little skinny wires that are getting backed up with some little electron buckets.
Yeah, I think we should just, like,
Hop into the Excel?
yeah,
Okay.
hammer out like problem one.
All right, let's do it.
Or
Oops.
just get to the correct, they want the total annual cost of power factor, average, standard deviation, minimum and maximum monthly cost.
All right, so I think we understand power factor. I'll take a minute